Hello everyone, Mr. Fawcett here, and we are about to start another Algebra 1 lesson. Today we're going to continue our discussion about multi-step equations, but we're going to take it to another level today. So we're going to do a quick mini lesson first. This is going to be similar to our combining like terms lesson on apples and oranges. Not the same topic, but the same short introduction to something before we get to some practice problems. So this page starts off with two equations. These are equations that we learned how to solve. Well, you may have learned how to solve them before last lesson, but these are two equations that would have been in the practice set from last lesson. So go ahead, solve them, and your solutions may look a little different than usual. So take some time to think about what those might mean, and then come back and play the video. Okay, so our first solution for number 1, we are going to distribute this 2 to both terms inside of our parentheses. So we get 6x is equal to 2 times 3x, which is 6x, plus 10. 2 times 5 is 10. Okay, there's no like terms on either side to combine, so I'm going to subtract 6x from both sides. 6x minus 6x is 0, so I get 0 is equal to 10. There's no x left, right? So all the x's ended up simplifying, and we're left with 0 equals 10. Now, does that seem like a true statement? Does it seem like a false statement? Does that look like a regular solution that we may have come up with? Well, let's hold on to that for a second, and let's do number 2. So for number 2, we have 3x minus 14 equals x plus 2 times a quantity x minus 7. So again, we have some distributing to do. And I'm going to get 3x minus 14 is equal to x plus 2x minus 14. So 2 times x is 2x, 2 times negative 7 is negative 14. I have some terms I can combine right here. So I'm going to go ahead and do that. I'm going to get 3x minus 14 equals 3x. Combine the x terms, leave the 14 as it is, so minus 14. I'm going to, there's a couple of things you can do here. I'm just going to subtract 3x from both sides first. So that gives me 0 minus 14, so negative 14 equals 0. And then we're just left with negative 14. So what does this look like? Now we have the same thing on both sides of the equal sign. Well, these are two special types of solutions. Okay, maybe you've seen these before, maybe you haven't. What this means, if we look at the one on the left, when we get two things that are completely different, so if we get something that's false, right? This is a false statement. 0 can never equal 10. So that is false. Whenever you get something like that, whether it's negative 2 equals 4, whether it's 5 equals 10, or whether it's something like this, 0 equals 10, this means that we have no solutions. There is no number that we can substitute in for x up here that will make our equation true. It's an impossible equation. There are no solutions for it. Again, this occurs when you get something that's different on one side of the equal sign from the other side. So when you get two different numbers on either side. Now, come over here. This equation right here is true, right? Negative 14 is equal to negative 14. There was another, I'm gonna rewrite this equation a little bit different because I think it's going to help for our discussion. But let's say instead of subtracting 3x, I had added 14 to both sides. So let's say I just add 14. So I get 3x is equal to 3x. Well, again, we have the same thing on both sides. But right here, I think it's a little easier for you to tell. It doesn't matter what you substitute in for x. This equation is going to be equal. right? If I substitute in 1 for x, I'm going to get 3 times 1 on the left-hand side and 3 times 1 on the right-hand side, and it's going to be equal. I could substitute in 4, and I'm going to get 12 equals 12. I could substitute in 7. I'm going to get 21 equals 21. I could substitute in 0, and I'm going to get 0 equals 0. Or I could substitute in -8, and I'd get -24 equals -24. So when you have the exact same thing on both sides of your equal sign, this means that you have an infinite number of solutions. So infinite solutions, and your solutions are all the real numbers. So all real numbers. We asked, why did we go over those categories of numbers, right, in our very first lesson? When would we need to know the differences between the categories? Well, this is one scenario, right? You need to know that every single real number works in this equation, right? So these are two special types of equations. One that gives you no solutions, and one that gives you infinite solutions. So some key takeaways down below. I guess I can make this a little smaller. I still want to show you the equations. Okay, so an equation has infinite solutions, or infinitely many solutions, with the solutions being all the real numbers, if you can simplify the equation down to an identity. So an identity is just when you have the same number or the same variable on both sides of the equation. So 1 equals 1, x equals x, 4c equals 4c, etc. So number 1 is like this equation, because we could simplify this equation down to 3x equals 3x. This is an identity. When you have an identity, your solutions are all real numbers. Now, it's better to put all real numbers than just say it has infinitely many solutions, because remember, there's different categories of numbers and they all are infinite, right? So the categories we talked about, the integers, the natural numbers, the rational numbers, the irrational numbers, and the whole numbers, all of those categories had infinitely many numbers inside of them. So if we just say infinite, that doesn't really tell us that we're talking about all the categories put together. We're talking about all the real numbers. So it's a better way to say our solution than just saying infinite many solutions or infinite solutions. Now, number 2 is more like the first one from up here. So an equation has 0 solutions if it ends up being a false statement. So we simplified this down here, right, to 0 equals 10. This is a false statement. Okay, there is no x value that we can substitute in that makes 0 equal 10 true. And you may be able to tell earlier in the problem that this is going to be a false statement. For instance, you may have been able to tell after our first step, after I distributed. So we got 6x equals 6x plus 10. You may have realized right here that, well, I have two 6x's, and it doesn't matter what x is. If I'm always going to have to add this extra 10 to the right-hand side, the left-hand side and the right-hand side are always going to be different. So you could have stopped right here and just said no solutions. It's just not everybody may recognize that at this step. They may need to go one step further and subtract 6x from both sides. Okay, so in our curriculum up to this point, we have solutions that can either be 0, 1, or infinite in number. So for now, the equations we work with will have either 0, 1, or infinite many solutions. And again, I want us to remember that infinite many solutions means all real numbers. You need to put all real numbers at the end of the problem if you have infinite many solutions. Okay, so that needs to be included. Okay, so that was our mini lesson. We're now going to go do some practice and put these concepts into action. So we're going to do numbers 6, 12, and 24 together. I would encourage you to, again, work on each of these problems before you watch the solutions and explanations part of this video. So let's jump down to number 6. And I also want us to be aware that there are many different ways to solve these problems. We talked about it in the last couple of videos, but you don't have to do one inverse operation before the other, right? There may be different combinations of inverse operations at work. The only thing is, the level of difficulty may be different based on which combination of inverse operations you choose. So sometimes it's a lot easier to add before you divide, or sometimes it's easier to distribute before you subtract. I know distributing isn't an inverse operation, but it is an operation we may use on one side of the equation. So I may go through some of these equations in a couple different ways. I may just go through them in one way. Just because you don't see your method up here doesn't mean it's not a valid one, right? As long as you use logical mathematical steps, you're going to be okay. And of course, you can check your answer with the one that we get on the screen or at the one at the bottom of this packet. Okay, so number 6, and right away we have a decision. We can either decide to distribute this -7 to both terms inside the parentheses, or we could do something else, and I'll come back at the end and show you what that other idea could be. But if we distribute, I get -7x plus 42. -7 times -6 is plus 42, or positive. And then on the other side, I get -7x plus 42. So right away, you may be able to tell, hey, this looks like an identity. I have the same thing on both sides of the equations, so I know that my solutions are all real numbers. And you could box that and you could be done for this problem. Okay, but maybe you don't recognize that right away. Okay, maybe you don't quite recognize that it's the same thing on both sides, and you keep going with your inverse operations. That's okay too. So let's say you subtract 42 from both sides. Okay, so this simplifies. You get -7x, goodness, is equal to -7x. Now, hopefully at this point you would realize, okay, these are certainly the same term, which means we have an identity and we have all real numbers as our solution set. Okay. This is one way to do it. Now, whatever way you do it, you're going to get all real numbers as your solution. Let me just show you one other way. Maybe you'll find it interesting, or maybe you just want to stick with this method where we distribute it first. Our other option was to divide both sides by -7. And again, that means we're dividing every term by -7. Again, the reason I did this was because right here we're multiplying by -7. So if I want to do the inverse, that means that I could divide. Once I simplify, I'm left with x minus 6 on the left-hand side. Over here, I've got -7 divided by -7, which gives me +1. So I just have x. And 42 divided by -7 gives me -6. So I get x minus 6. And you'll notice I still have an identity here, right? X minus 6 and x minus 6. Now you could keep going and do some more inverse operations, right? But then you're just going to get x equals x. So whatever way you do it, your solutions are going to be all the real numbers. Okay, it doesn't matter what identity you get at the end. It just matters that you get an identity. All right, let's move on to number 12. If you'll notice, I guess before we go there, these first 4 problems were pretty straightforward. They were more so like problems from the last lesson. So 1 or 2 steps. Actually, these are all at least 2 steps. but they're some of the simple ones. Let's get on to 12 though. 12 looks a little different. Now, 12 isn't any harder, it's just a little longer. So there's nothing in the problem that we haven't done before. We're just going to have to be applying more steps. And when you have more steps, it's absolutely critical that you keep everything organized. And it's going to likely be better to show more work than try to skip steps. Maybe you're not skipping them in your head, but on paper you're skipping them. And that's kind of just a recipe for you to miss something in the shuffle somewhere. So the first thing I notice is that I have two sets of parentheses, so I'm going to have to distribute twice. So I'm going to distribute here, and I'm going to distribute here. You can do this in 2 steps, you can do it in the same step. So I get negative 7b plus 14, because negative 7 times negative 2 is positive 14, minus 8. And if it helps you to draw this line down the center of your paper, let's do that in a different color though. Do it in black. Feel free to go ahead. Just make sure you keep everything on the right side. Not the right side is different from left, but the right is in the side it's supposed to be. When I distribute my negative 9, I get negative, let's put an equal sign there though, negative 90 plus 45b. Then off to the end, I have minus 4b. Okay, so again, check the distributing, check your signs, etc. Make sure you have the right ones. Now I'm going to do some simplifying. I'm going to simplify the left-hand side. I've got like terms, 14 and negative 8, so I can simplify those. So I'm going to get negative 7b plus 6. Okay, 14 minus 8 is 6. On the other side, I have 2b terms, so I'm going to combine those, and that's going to give me negative 90 plus 41b. So again, nothing different from other problems, we just have more steps. I'm going to move my 7b to the other side, or my negative 7b, and I'm going to do that by adding. So add 7b to both sides. Keep your equal sign. That is going to give me 6 is equal to negative 90 plus 48b. Okay. I'm then going to move the negative 90 to the other side by adding. So add 90 to both sides. That is going to give me 96 is equal to 48b. We could put a little bar up there as well. Last step is to divide by 48. So divide both sides by 48. And that's going to give me 2 is equal to b, or b equals 2. So we had to distribute twice. We had a significant amount of inverse operations, but that's all it was, distributing and inverse operations, as well as combining some like terms. Okay, I'm not going to do this problem in a different way. There are definitely some different combinations of inverse operations you can use, but we could also be here all day with going through all those. So we are going to move on and finish with 24. 24 is going to have some fractions, I believe, but that's okay. We can handle them. Okay, so again, different type of problem, but only in that we have fractions rather than integers. Okay. A couple ways you can do this, and we will do this 2 ways. I know this video is going to go a bit long, but we'll hopefully keep it to about 25 minutes. I think it's beneficial that you see the different ways you can solve fraction types of problems. So the first way, and I'm actually just going to rewrite this, make it a little easier to maneuver. So I have 5/3 is equal to 9/4 n minus 8/3 n. So the first method you can do is try to get all of the denominators equal to each other. So whenever you have an equation that is made up of only fractions, you can work to get the denominators all equal to one another. And this also works if you have whole numbers. Just know that the denominator is equal to 1. The common denominator between all three of these is going to be 12. So I'm going to multiply this fraction by 4 over 4, because that's going to get my denominator equal to 12. I'm going to multiply this fraction by 3 over 3, because that'll get that denominator equal to 12. And I'm going to multiply this fraction by 4 over 4, because I need to get that denominator equal to 12. Okay, once I do this, I just multiply straight across. So I get 20 over 12 is equal to 27 over 12 n minus 32, oops, let's get rid of that, minus 32 over 12 times n. If you have an equation where it's just made up of fractions that you're adding or subtracting, you can get rid of the denominator. Okay, and the reason, so technically you can just cross these out because they're all going to be able to simplify, and you're left with 20 equals 27 n minus 32 n. But let's dive into why that's allowed. Why are you just able to get rid of the denominators like that? Well, think about the inverse operation for simplifying a denominator, right? You would multiply by whatever the denominator is. So if I multiply each of these terms by 12, that will simplify each denominator, right? And that's allowed because if I multiply everything by 12, that's like multiplying both sides by the same number. So I get 20 is equal to 27n minus 32n. And then this equation should be pretty straightforward. Combine my like terms, I get negative 5n, divide by negative 5, and I get negative 4 is equal to n. So that's one way we can approach this. We can try to get every denominator to equal the same thing, and then that essentially lets us get rid of all the denominators and just have an equation with integers. Let's look at a slightly different way. And this is the way I tend to approach the problems, but again, just because I approach it or I think it's a little easier doesn't mean you're going to always think it's easier. We're still going to find common denominators, but I'm only going to worry about the side where I need to combine my fractions. So I don't have to worry about this side right here with the 5/3 because there's nothing to add or subtract on that side, right? I do have to worry about combining these two fractions right here. So you can just think about finding common denominators on the right-hand side, which it's still going to be 12. All right, so I am going to multiply this equation still by 3 over 3, and, sorry, I said equation, that fraction by 3 over 3, and this fraction by 4 over 4. Once I do that, that is going to give me 5/3 is equal to 27 twelfths times n minus 32 twelfths times n. And again, we've already done that. Now I can combine these two fractions on my right-hand side. So I just add or subtract the numerators, which is going to give me 5/3 is equal to negative 5 twelfths n. And whenever the n is off to the side, you can also just put that right in the numerator, right? Because when you're multiplying a fraction by a number, you're multiplying the numerator by that number, not the denominator. Like quick side note, but if I have negative 5 twelfths times n, this is never equal to negative 5 over 12 n. right? That's not true. What's true is negative 5/12 times n is equal to negative 5/12 times n over 1, because if I turn n into a fraction, its denominator is going to be 1, and then I multiply straight across, and I get negative 5n over 12. So sometimes you'll see the n's written outside of the fraction or off to the side, but you can just stick those right in the numerator, okay? Multiply the numerator by whatever that variable is. Okay, coming back down here, whenever I have a fraction equaling another fraction, there's a very easy way to solve. You may or you may not have seen this, but it is called cross-multiplying. Okay, so I multiply 5 times 12. I'm going to put this over here, which gives me 60. And then I multiply the numerator and the denominator, the other numerator and denominator, which gives me negative 15n. What this does is it gets rid of, or it simplifies the denominators out for you. So it gives you a nice equation with just integers. Then you can divide, and we get n is equal to negative 4, which is the same answer we got using our other method. Okay, we will hold off on any going through this problem any other way. If you have a question on cross-multiplying, if you have a question on what we did here with adding or subtracting the fractions, finding common denominators, write those questions down, because I do want to get to them. We're just running a little late for this video, so we'll hold on to those questions for a future discussion. Okay, this is Mr. Fawcett. Enjoy the rest of your day, and I look forward to seeing you next video.